like with the streamers actually.
Yeah.
Just 'cause it's like live.
Over here is better. The quality on this one.
Oh, it's just the TV.
It just shows this.
How is it like live?
Yeah, you can go on stream right now. It's aiming at that corner. It's kind of live, like ish live.
Okay, so it's like half a minute delay.
Only forever behind.
I mean, that's another thing too.
Okay. Hi everybody. We're starting our last week build series. Right in front of you here is the antenna platform that we're finishing tonight. We got that built this afternoon, and then Alex is going to help us test this thing and put his electronics to work that he was working on down at Georgia Tech. And today we're going to be initializing the phase comparison system. So actually starting to try to calibrate this thing and get it to give us some values for direction and heading of the beacon, which we also have here.
Yeah. Everything was looking good with test equipment down in Georgia. Now that we have the actual beacon, we can see how it'll work in the real world. But yeah.
Alright, so we're going to get started. Over here, we've got a grid kind of set up. Adjust my camera here. We've got a grid set up where we're going to do some tests. And these tests are going to allow us to use the phase comparison system once everything's wired up and test it using what's called correlative interferometry, which is basically we're going to take the antenna platform, which I will bring over. And once it's set up electronically, we should be able to calibrate it by moving the beacon around it at different placements.
Okay, so you got a 9x9 grid set up here. So we'll be able to set the beacon in each spot, read out the 4 different measurements we get for the phase differences, and then create a database of those that we can use to compare values later. So that if we can get an array of all the values that we'll read at different positions, then when in the field, when it reads a certain value, it'll compare it to that array, find the closest match, probably through some sort of least squares method, and then determine its location from that and navigate towards it. So.
Cool. Alright, let's get this thing cut.
You switch cameras with this.
I was going to, but the GoPro isn't hooking up, which I've had that before happen. I have the wrong USB cord, so we're stuck with that view, but that's okay. I guess next up is I will set up the antennas, as in screwing them into the base, and Alex can start setting up electronics and get a laptop prepped for.
Do we have
that.
the holder for all those PCBs now?
I do not yet.
Alright.
In fact, I haven't even started printing it. That should be ready tomorrow. That's after we get some values. I'm going to let you do the rest of the calibration. I'm going to work on that.
Alright, sounds good. So I'm going to get the computer ready while you get those in. Then I will get in, and I'll get the electronics ready right now too.
Do you need on power?
Yes. No. No, it'll just
Laptop
be on the USB.
Be able to cook for a little bit. Okay.
Leave it for now.
Let me know if you need a power harness over there.
I'm going to do it without the amplitude measurements right now, just because the other ones had a slightly higher gain, just while we're testing, and then if everything works well, then we'll try it with lower gain as well.
Sounds good. Alright. Did you want me to try to find some nylon screws to use near the antennas?
Yeah, ideally. less metal possible around it.
I will try to find those. Still on the tip of those screws. Don't break them. I might see if Josh knows where they are. But I might have some too. Okay, I might have to strip them from my robot. Ah, yes, I have some. pound screwdrivers. Let me know if you need a drink.
Alright. What do we want to do for connecting all these powers though? 'Cause all of these need to get the same 5 volts. We only have one 5 volt output on the Pi. Or on the Arduino.
We will
Just gonna
have
need to, like,
to
solder it all.
somehow split that.
Yeah.
Because running it from the Pi would work,
Mm-hmm.
but you said you only have one 5 volt output?
Yeah, there's either 1 or 2. Not 4 though.
Just quickly self-tapping and setting nylon screws to get these antennas in place. I went to go get a bigger screwdriver and need a smaller one. So they don't want to self-tap because the holes are too small, so I'm going to have to actually tap it with a metric tap system. So we're going to go at it a little bit with this. So yeah, while I'm working on this, Alex is working on prepping some of the wiring
Yeah.
and primarily concerned right now about getting an ideal voltage source because there's not enough outputs for every board to get voltage from the Arduino control board. see what I've done here is essentially just added, hoping this will be focusing on stream, these two nylon screws here, chosen for plastic to stop any possible interference with the base of the antenna, just to mount those into the antenna platform. So, yeah.
Okay, get the. Where's the fan for the soldering?
Over behind the laptop, over here.
Perfect.
You might want to go this way. There might be room to go this way. Alright, this antenna's on here, good. It's one down.
Nice. taking one of these for us. Taking these little pin headers. Yeah, that's okay. Taking these little pin headers and just soldering a bunch on the bottom ones all together so that they're all electrically connected. Kind of like a hacked way to do it, but it's not very professional. But yeah, it'll work for testing. But then anyway, we can just take the single power output pin from the Arduino, attach to one, and then use the other four to get power for each of the four individual circuits. So doing that with both the power and the ground. That's how we'll be able to power these for testing. And then once everything works, obviously we'll get a more robust system going.
Did you figure something out for the power harness yet? Or
What?
figure something out for the power harness yet? Or?
Yeah, that's what I was just explaining.
No, I missed it. I was too busy paying attention to Mike.
Yeah, these. So I just soldered all the bottoms, so now they're all electrically connected. Put one power and then the others out.
Sick.
So it should work, but I mean, it's very like hacked together. But
I can't believe that bridged.
yeah, it took a bullet of solder.
No, that was a really good idea. I appreciate it.
But yeah, so they should be good now. And I just gotta hook them up. But I might need to switch these cables. No, just a test for these. Alrighty. Should we switch the camera to be like? How do I switch the camera to be? Or do you want it down here or over here? What?
I'll put it down here.
Okay. Do you want me to change it or?
I'll move it. The tripod's kind of funky. So.
Gotcha. That's fine.
Alright, and I've got a second antenna ready. That's 2 of 3. You got a nice big frame.
Nice.
So now you'll see we got both of these antennas ready, and we're working on the third. And Alex is gonna get the electronic system wired up to put to use. if you've joined us recently, we have been preparing the antenna platform to be hooked up with the phase comparison circuit that Alex is preparing for our first calibration tests, I believe would be the right way to put it, of our navigation system. So, prepping the antennas to go onto the platform. Ooh, Brian did say that the Arduino expansion board has a 5-volt splitter.
What's the expansion board? Is that this blue one?
I think it's the.
Unless it's this power supply board.
I was just say
on
you
the
might mean the
breadboard.
power supply board on the end of the breadboard. Wow. Hi, you were recommended this channel. Well, hi, welcome. We are Eggman Robotics, a team of undergraduate students from around the U.S. from 4 different colleges. Those being Embry-Riddle Aeronautical University, Georgia Tech, Kent State University, and South Plains College. Those being from Florida, Georgia, Ohio, and Texas. And we are working on EGgBOAT, which is an autonomously guided boat that delivers emergency supplies to a radio beacon worn by astronauts of the Artemis mission. And this challenge was put out by NASA's Micro-G Next. So, and they provide challenges based on the Artemis mission for teams of undergraduate students around the country. Oh, I just kicked it. Let's see. Nice to know it's rugged. I'm just about ready with the antenna platform. So
I'm pretty much ready with this.
Alright, Alex is just about ready with the electronics. What I've got complete here is the antenna platform. For those of you that have seen EGgBOAT, this is not just our boat. This sits on top of our vessel, and this is going to be our antenna kind of triangulation system platform up here that's going to allow us to gather signals from NASA's radio beacon called the Angel Beacon. That's this right here. And based on where this is, hopefully based on these and Alex's phase comparison circuit that he built, we should be able to reference at least some calibrated values to find out where this is. Cool. I'm going to keep my phone out, try to answer some questions and see some comments.
Nice thing also is if we switch the final one over to the nano, where is it? It's just here. Here it is. The Arduino Nano has 8 analog inputs, while the Uno only has 6. So we'd be able to get all the values from the amplitude measurement ones as well.
On just, so that's 7, right?
Right, so the Uno's one short, but the Nano has all of them. I mean,
Gotcha.
the code runs exactly the same.
Yeah, right.
The only thing I don't know is like how much memory, but that'll depend on how big the code ends up being.
Gotcha.
Bring this stuff over.
I've lost a screw, but I'm not extremely worried about it. Cool.
Alright, I guess we'll show this first. Right now it kind of looks like a mess because there's so many wires everywhere for power and for the analog reading. But really at the bottom of it is we have the Arduino Uno, which will read the signals and control everything. But then we've got the center board, which does our phase comparison, and 3 identical amplitude boards, which are all, designed by us, and I was able to create down in Georgia Tech. So here's a look at the amplitude board. What it does, it takes in the antenna right here. It will filter through a bandpass filter for only the 121.65 megahertz signal. It'll then amplify it with just a standard RF amplifier and filter the noise out of that amplified signal, leading to overall a gain linear of about 7 to 8 with testing. So we have 3 boards, 1 for each antenna. Those all go to the center board, which does the phase comparison. It'll take those sine waves that have been amplified and run those through a comparator, which will take it to a 0 to 5 volt digital level, meaning all the positive halves of the sine wave will go to a square wave where it'll be the high value of the square wave, and all the negative halves will be the low value. All those square waves will go into the high speed phase comparators to compare both antennas 2 and 3 to our reference antenna 1, and those will output square waves with varying duty cycles depending on what the phase difference is, and those square waves with the varying duty cycles will go to an AC to DC converter, which will take the average value, which we will read with the Arduino, and from that be able to infer and calculate where what the angle differences are. But yeah, so now we're just going to get it all hooked up. Alright, so we've got this top one goes for antenna 1. That's perfect. I'm gonna move this. Is everything done being secured for the
Yep.
platform? Alright, I'm gonna put it in place in the center. Alright, so we've got this grid here. Talked about it at the beginning of the stream, but it's just 9x9 grid. Each dot's about a foot apart. We'll put the reference antenna at the center, and then we're gonna once we get everything set up, so we can start doing some testing, we're gonna place the beacon at each of the different dots on the 9x9 grid, measure the 4 analog outputs of the phase comparison circuit, and then move it to the next grid cell and do it for all of them. And hopefully we'll get unique values for each that we can use to refer to create a data set. So it will, in addition to the hopefully accurate mathematical model, we'll be able to look at this data set to reference what the current value from a certain reading is, and then reference the data set to calculate where the beacon likely is relative to that front antenna, both in distance and in direction.
So for your system, the front antenna is still going to be on the center of that X as the reference
Yeah.
antenna?
Yep. That'll go into antenna 1 in the phase comparison circuit. And there's two phase comparison circuits on the board. One will compare antenna 2 to our reference, and the other will compare antenna 3 to our reference. And our reference is just antenna 1. So that'll give us values of, we'll just take the angle for antenna 1 to always be 0, and then antenna 2 and antenna 3 will have angles relative to it. Two is on this side. So because we didn't have the transmitter during the development or during the full development of these boards, and especially at the later stages, we haven't been able to do full tests on them. So this will be pretty informative. We were able to do tests with the amplitude or with the amplifier board variant that has a peak hold circuit to measure when we get very close. And that was working last night, but it only worked at extremely close distances. But the values it was reading was identical to what we were reading on the test equipment, which was just oscilloscopes and using function generators. So that did give us some pretty positive results for how this will turn out relative to the test equipment, which will hopefully be pretty similar. Okay. Alrighty. I need a doctor. Everything good with the stream?
Yep.
Stupid computer case gets in the way of the adapter. To take off the bottom of my computer case every time I need to use a USB 2 or whatever.
It's highly convenient, don't worry about it.
Alrighty. now just writing up some C code to run on the Arduino to read out the values. Pretty simple, nothing huge.
Cool. We are working on the antenna platform right now. For those of you who have joined recently, the antenna platform is the hub of all navigation for EGgBOAT. So this is really our first test to see whether or not we will be able to do some direction finding with this thing. just a quick recap to those watching. Alex is programming some analysis hardware so that we can do some readouts on the phase comparison navigation circuit that he built.
Yep. Just it's not too nothing super fancy right now. Just defining all the pins, just doing analog reads on each of them, and then just outputting them in a nice way that it'll be easy to read. So.
And if there are any questions about EGgBOAT, the navigation system, or the boat itself, or any other part of the NASA Micro G Next competition, please drop those in chat. We'd love to hear from you guys and answer any questions you have. While we're on YouTube. That's crazy.
The whole 12 people. That's when we started.
Sick coding montage. Imagine if you had the ability to just make like montages instead of like actually doing lengthy things. Like it just showed up as a montage. Be pretty cool.
This says it should work. Aha, look at that. We've got numbers,
Nuh-uh.
live outputs.
What the? Wait. This is not enough.
It takes like a minute to start up.
Okay, so in order of those four, what are each?
1, 2, 3, 4. So 1, 2 are the two for comparing the.
Why is the second one so small?
3, 4.
Oh, it's doing things. Go ahead.
Is it 50 millivolts? Yeah, it's gonna take a minute before it like starts outputting the normal. I don't remember what the values were originally, but.
So just as an update, we don't currently have this shown. Gonna do it in post now. That'd be great. So I don't currently have this shown on screen because Alex is doing it on his laptop, but he quickly programmed something to analyze all four channels output by the phase comparison circuit, which are two voltage numbers that correlate with the phase offset from these two antennas, and then two more voltages that correlate with the phase offset for these antennas. Is that right?
Right.
Okay. And he kind of was just figuring out the display sequence for that. So it's just a cycling baud rate refresh system in the Arduino coding suite that kind of just refreshes on each value. I don't know, every fast, like, I don't know, thousandth of a second, hundredth of a
now
second.
we're getting values cycling through. Different values. That's something. I don't know why it's only sent. Oh, that actually I think that might be just how the beacon works. It only sends it every so
I was
often.
gonna say that is the pulse, isn't
Right.
it? So
yeah, when I was testing this we had this for what? It got sent to Embry-Riddle at first, but then I got it up in Georgia Tech for about 2 weeks. So of the time I was able to work on it, I was able to spend probably solid 3 or 4 days using it, and it was mainly for testing just the signal that we'd be receiving on the antenna. Because up until then, I was building the antennas based on just theoretically how they should work, and then testing with it's called a nano VNA vector network analyzer, which would tell the properties of how well it'll be receiving a signal at a specific frequency. And everything seemed fine, but we hadn't had a beacon to test it, so when we got it, that's what we were mainly doing. And then testing the filtration and the amplification as well. But at the point that we had it and then we had to send it back, all we had was the initial filtration, amplification, and then post-amplification filtration, which is everything on the individual amp boards. So we were able to test those with the antenna and see that everything was working well. But really how it is working is that it's just sending out the 121.65 megahertz pulse every couple, about every second. it's not a constant signal.
Yeah, so every time this beacon lights up, you should be able to see that on stream. It's pretty bright LED. Every time that lights up, a pulse is sent out from the radio beacon. So prior to a lot of other radio signals, like, say, I don't know, radio stations that you might receive in your car, and things like Wi-Fi or things like RC channels for remote control vehicles, those are constant outputs of a radio signal, as to where this kind of operates in a pulse, where every time the light blinks, a new pulse is sent out of that, like a burst of that frequency. So
Yeah, so we're reading the 4 output channels right now. It seems that when it's not getting any value, when the antennas aren't receiving anything, the outputs are 658, 10, 10, 658. These are values on a scale of 0 to 1023, where 0 represents 0 volts and 1023 is 5 volts. So really, to get an approximate value of what the voltage output is, you can multiply by around 5 millivolts. So we're getting about 3 volts, close to 0 volts and 3 volts, which really is the, it's actually the, while we're powering EGgBOAT in general on 5 volts, all the circuits run, they take that 5 volt signal and convert it to 3.3 volts, because that's what all the chips run on. So really what we're getting are just solid 0-1 outputs before it receives the signal, which makes sense because we're outputting from the digital logic circuitry. And when it's not running, we're looking at the 2 outputs will be opposite, I guess, and one will be 0, one will be 3.3. When we convert those constant signals into the averager, it's not really doing anything, it just leaves it at 0 and 3.3, and that's why we're getting about these values. So, but yeah. Alrighty, now time to look at it. How do we do that? Just an interesting test. Can we put that back here, maybe, just to see what changes? I want to see if. Okay, so it's definitely like changing all the values because we were consistent. I guess I'll talk to Slaughter. This is, we're not looking super in depth yet. Kind of just seeing what everything's doing. But whenever the signal is received, I was just looking at output 4. And every time the first value would always be about 252, be 252, 253, or 254. Now we moved it, and it is consistently not that. It is now 135, about 138, 136. So we're definitely getting different value outputs depending on where the beacon's located. And when it's in a certain position, we're getting consistent values, which is really good because we had no idea. There is no indicate. Well, besides all the testing where it was working, there was no like very strong indication that it would still do it with the beacons, because we hadn't even had a chance to do any of the phase comparison testing, even like whatsoever with the antennas. So even that we're getting some difference based on location, and those different values are consistent, is a really, really good sign. So yeah, we're balling right now.
yeah, so prior to this, there was a large period of time, that being between around mid-March till now, which was a month and a half at least, where we did not have the beacon. And that was definitely where most of the development of this circuit, at least in the phase comparison end, right?
Yeah.
Was being done. So without the beacon, the only way to test that was to utilize a function generator as the source of the signal, and then use an oscilloscope to read those voltage values output. So it was kind of, you had to self-manipulate the signal, which meant that we were never really sure how it would act in the real sense outside of theoretical.
Right. There's 2 main phases that I guess 4 phases that went into the development of this board. So the first was early in the semester throughout February, some of January, mainly February, and very early March, where I was building and testing the antennas. I had no prior experience, nor did anybody on the team with antenna development. So this was a lot of testing and just guessing and doing research, but eventually got it good. And then from there, went into the second phase, which was the filtration and amplification. This was also a completely new thing because I didn't have any experience before with any RF engineering. So any if you have experience making filters, there's pretty well-known topologies that you can do, and you can mathematically calculate what values, what frequencies will be attenuated or passed through based on your chosen component values and that topology. But at extremely high frequencies, the component values aren't just the rated component values. Parasitics start to factor in. The shape of the board itself starts to factor in. So nothing was working as intended. So that had to be a lot of testing and different versions with prototyping to eventually get the filters working. And this second phase, which is most of around spring break, this is the one where we did have the beacon. So we were able to test to make sure that the beacon, the signal received from the antennas by the beacon could be effectively filtered and then amplified and then filtered out of the remaining noise. So that was the end of phase 2, and that's when we lost the beacon. Well, we didn't lose it. We had to send it back to NASA. We lost access to it. I didn't want to make it sound like we actually stuck it under a chair and didn't realize it was there. Yeah, no, we dropped it in the ocean. Yeah, we had to send it back to NASA. And phase 3 was initial development of the phase comparison. We didn't need the beacon for this. This was just trying to figure out how the circuit would work and to try to get things working on an individual sense. First, we need to make sure we could get it the variable amplitude depending on distance that received AC signal. We need to make sure we could get it to square wave. We need to make sure that the phase comparison topology would work in general, so prototyping at lower speeds on a breadboard. So that's what I was doing most of the phase 3, and I didn't need the antenna or the beacon for that, which was fine. But phase 4 was the past 2 weeks, and that was probably 40%, 50% of all the time into this, and that was the full development of the phase comparison board, as well as combining all of the other filtered boards from phase 2. And this is where the beacon would have been really nice, but we didn't have access to it until yesterday, or 2 days ago. But that was after all the boards had already been finished. So yeah, so we didn't have that for a while, but now we do have it. And the good thing is that all these boards that I was making down at Georgia, they were all working with the test equipment, with the oscilloscopes and the function generators. But we weren't able to have the real thing. But now we do, and it seems to be working the exact same, which is really good. But yeah, getting consistent starting values. Yeah, all right, this is nice.
So I did some tests. So as you'll note right now, all of our electronics are on the floor, which isn't exactly optimal for a boat. We can't just have them laying on top of the boat. That'd be prone to water and be bad, very bad. So in lieu of having them outside of the system, what I'm working on right now is finishing our 3D model for the navigation components box, which will sit here. There was a prototype part for that made, but didn't include a box for electronics. So when this is entirely done, there will be a box up here that gets mounted to screws that already exist that will hold all of these components in a nice fashion up front. And those wires will then be able to be sent down into the main hall for computing on the Arduino in the control bay. And what's nice about that is it looks like I exported what I have right now, which is about, 70% of this part. And it is only 5 hours print.
Nice.
So overnight to the afternoon would be plenty. So by the time we're ready for a water test, that'll be done.
Yes.
Prep.
That's good.
The only thing I have left to do is put a lid on that side, but I want to make an extended lip around it so that we can put one of those gaskets out there for waterproofing. because I'll probably have just a screw lid on top so we can
Mhm.
access the components. But then when I screw that down, I just don't want it to be plastic on plastic. I'll put a gasket in the middle of
Okay.
that for waterproofing, and then
How do you make that?
it's just like I'll do. You know how you sweeped your antenna engraving for the
Mhm.
antenna slide in? Very same thing for the gasket, just a round sweep
Okay.
remove for the gasket line. That looks like, I'll get a part. Looks like this. So previously this was our top box for the antenna platform. This kind of sat right here. You'll note that it doesn't really fit with the new antenna, so there's a new one that makes room for the antenna and has a box on top for all of the components. The gasket line looks like this. The gasket kind of sits there.
Oh,
between-
gotcha.
And if you look like
Is it different material?
Yep, it's a rubber gasket line. I have a bunch of it.
Oh, okay. It's not 3D printed.
Yeah.
Gotcha.
So,
Just for waterproofing. Nice.
yep, and then it kind of just squishes down on it.
Perfect.
Yeah.
That's awesome. All right. I'm gonna have to figure out how to export all of this data because I do not know that yet. But I'm gonna disconnect this for now. I think we probably turn this off. I'm gonna do
Fair.
some work on getting all this data set up. But the process will be, it's kind of described earlier. Hoping to we're gonna put the transmitter at each of these different little dots in this 9x9 grid. Each one's about a foot apart. Then we're gonna take a couple. We're gonna read the different values, maybe like a second's worth, 10 seconds worth. Average them out and get values for each of those 4 dimensions, which are the 4 analog readings. Do that for each location, and then we'll have a data set that we can compare to. We can compare unknown signals to in order to determine the location of the transmitter. So that'll be one way that will probably work pretty well. Another way that not sure if it'll work is just converting the measurements into angles and then using that to just mathematically calculate the position. Theoretically, if this system was perfect and there was no propagation delay in any of the components and everything worked exactly as an ideal component would, that would work perfectly fine. That's obviously not the case, so we will adapt to however the readings are. Alright, I'm disconnecting this for now. Alright, that's actually really great that those values were different. That is like, passing that test is like okay, we can do this. This can actually work really well.
Yeah.
So, that's kind of
So,
I didn't even realize it at first that, wait, this is it. This is
Yeah.
it's working.
so that what's kind of funny is we were kind of how do you want to word that? We were
We're not sure if this is gonna work at all.
Yeah.
Because we're not able to ever test this full system, especially with the beacon and with the antennas and comparing them. It's just each part was tested individually, and usually everything breaks when you integrate it. But this actually worked. I mean, I'm sure there's still tons of work to be done. We might encounter a bunch of other errors, but the fact that we got consistent measurements at one place and then changed it to a different location and got different measurements that were still consistent at that location is a really, really good sign.
yeah. So
So-
I think while we were working here, we were kind of desensitized to
Yeah.
the accomplishment that was just made.
Yeah.
Seeing different values and those different values being constant from different antenna placements is pivotal, because that shows that there is at least some amount of indication of difference in the phase comparison circuit that we should be able to convert into directions.
Right.
The 2 ways to do that based on how that would work is the first one, since each offset should be measured similarly to the front one could say that in a perfect world, balancing those 2 offsets would be a way of finding the direction, the primary, straightforward direction of the beacon. But that's not always true.
Yeah, that was the method that we proposed in our
Yeah.
original proposal to NASA that got us accepted to this stage. That you can there's a mathematical algorithm that you can that we created that can be ran, and given a set reference antenna, the two angles to two other antennas in an equilateral triangle, you can find the position of the transmitter from anywhere, not just the angle towards it, but its exact position relative to the antenna. So
That's right. So the other convenient way to do this is if the values aren't exactly predictable at different placements along this grid, say, you know, we can't make it into an equation where we can change the offsets to be equal to find the direction. The other way to do it is called interferometry, which is basically based on each of these grid points, you lay out the beacon, and since we know that at that point there's a constant source of signal, there's exact offset values that are being generated from the different phases, we can log those and then allow the computer to reference those in like a spreadsheet that would provide some data that would be able to reference it and tell it, hey, the beacon's over there where we tested that direction. So
right, like a very high-tech form of calibration.
that's right.
So, but yeah. That's sick though. I'm gonna run the restroom.
Okay. And while Alex is going to start tuning this system to actually give us directions and distance to the beacon, which he is very hopeful on right now based on the promising results of such recent rapid tests. While he's working on that, I'm finishing up our control box up top yet again. So doing some measurements on the amplitude boards and putting those into the box design. Sweet. What's really also satisfying about such accomplishments here is that parts of the system were made in many different places. The structural framework for this was laser cut, these wood pieces that you can see just recently this week at me, Alex, and Josh's high school that we were enrolled at, known as iSTEM. Shout out to them for letting us laser cut this this past Monday. That was very useful in getting this step. And as you can see, manufactured quite the aesthetic looking platform here. And so thanks to that, we've gotten parts from Ohio. Some of the 3D printed parts on here were manufactured in Florida. Those were brought up. The PVC piping for the front mount was created in Texas. So all of these parts have come from somewhere different, and of course the electronics coming from Georgia. We literally have, even just here, just for the antenna platform, parts from all 4 states that we have students from. So it's very satisfying to see that kind of come together and actually get good results. We were kind of not criticized, but we were warned, say, of our intercollegiate status. Like, hey, you guys, you need to be very careful with what you're doing because it's not always easy to keep a team in check, you know, across such distances. And we're like, yep, we know the risk of being apart, but we also knew that when we pulled together the right team that we would be able to get it done. So shout out to all the guys. Eggman Robotics. Let's go.
you see that comment?
Happy that the Weeb family is enjoying the live stream. Happy to have you guys. Brian better be moderating. According to my calculations. Oh.
The nice thing, I think the best way to do the calibration, we can put timestamps on the outputs here, and then I think if we just start the code and like a video recording at the same time, we can get timestamps and like compare them to see which one, like what positions correspond to which code, because it just goes too fast, like to see it live. So like we'll run it, put in each position, get the outputs, export all that data, and then compare like the timestamps in the video, like of which location to the timestamps in the code, and then write it down there. Because it just like the values go by so fast that I don't think we could. Like
Yeah, I'm
those.
trying to think of a way to log it. I mean, we could like. Because the weird thing about that pulse is even in the pulse, there's some variations in values at like
Yeah.
the start and the end.
But it's also right now we're only sampling 10 times a second. We could always increase that just to see what
More.
that looks like as well.
I feel like it seems really tedious
Mhm.
to do it that way, but it might just be the right way to do it.
We're only gonna have to like also just look at like for each part, like all the data is gonna be in order. So we put in that if we put in one of the cells, we see that's at 1 minute 53 seconds. Just scroll in the data till we hit 153, and then just
Yep.
look at that data there. I can't think of a better way right now.
You
If
just
anyone
want to.
on stream knows how to do it better, then
Yeah. This is kind of a.
I mean, it'll definitely work, but I don't know.
Yeah,
More
it's
efficient
a
way.
tedious route of documentation, but other than having I'm not really sure how to have the Arduino document this.
Yeah.
It's. to
I
have
gotta
it
also
right
see
there
how we
itself.
can export the data. But I mean, I know we definitely can do that. I just gotta figure out how and what kind of format we can export it to.
Because I mean, the one really, if you want to do video references, the one really easy way to do that is, like, I put my phone, I don't know, there, and let it record
Yeah.
in a low quality format so I don't explode the phone.
Yeah.
But let that record and start recording, and on your laptop, we can download OBS really quick if you don't have it. That's what I'm using to stream, but that lets you do screen recording very easily, and lets you just like write that to your computer. It's
Mhm.
kind of like a screen recording.
Well, the thing
method.
though is that if we do it that way, we're not gonna have like the data values to average out because they're not gonna like we saw that there's slight variations.
We would be hand putting in the data values.
Yeah, I'd rather not do that.
Yeah, if you think you can
That seems
export
more
it in
tedious.
some amount of way that
Yeah, I'll
lets
look up.
us, because we just have to. If you can export all of that,
I'm pretty sure we can because there's like a button to toggle on and off timestamps. I don't think they'd have that if there's no.
oh, if it can save timestamps, then
Yeah.
sure. I was gonna say, I mean, you can write it into the code that you just delay and a for loop that just adds every.
Yeah, I'll figure out how we can export that.
Okay.
We have a question. Do all 3 antennas report something different? Let me get in the camera. I'll
Yeah.
take this one. So how it works right now, we've got the first antenna is our reference antenna. That is the one that we will compare the other 2 antennas to. So really what we're looking at is the angle on each of the antennas. We just arbitrarily assign the first one to be 0 degrees, and then we find the angle difference for the other two. So what the circuit does, after it amplifies all of the and filters out the signals, we have two phase comparison circuits. The antenna 1 goes into both of them. In the first phase comparison circuit, the other signal being compared is antenna 2, and in the other one, the other signal being compared is antenna 3. So we get 4 outputs total. They are, for one of them, I guess the first, it's 4 outputs total, 2 pairs of outputs. The first pair is the difference between our reference and antenna 2, and the other pair is the difference, or gives us information about the phase difference between our reference and antenna 3. So we get 4 outputs total, and they both, those 4 are 2 pairs, and each pair correlates to the difference in phase from one of the back antennas to our front reference antenna. So that's what the system's doing.
So to sum that up, we've got 3 antennas, which by the end of the circuit output 4 voltages, which give you 2 phase offsets. Alex, you know what the hardest part about this 3D modeling is?
What?
Making it look cool. That's not a joke.
It'll look weird otherwise.
Yes.
You worked on the slots for the boards?
Yeah, the housing for it.
Gotcha.
Yeah, it's very, very awkward. Did you measure this out as a 6-inch grid?
It's 1 foot.
Oh.
Distance between like the centers of each piece of tape.
Oh yeah, I'm oblivious. That's definitely a foot. Yeah, that looked like 6 inches.
I'm like the same.
What time is it?
It's 10:40.
Feels like 2 a.m. Let's see. Pop quiz. What is this? First person to answer wins nothing. You'd have to really be paying attention to stream to actually have caught that 5 seconds of.
Anybody's watching it that closely.
People got it on in the background while they're playing pickleball. Guaranteed. It's the only pickleball time passer. And do you want me to make the box for the amplitude boards?
Oh, the other version?
Yeah.
Yeah, would we be able to have like 2 boxes, one for each? Like one for if we use one with the amplitude and one if we don't.
It would be a very similar box, so
Okay,
yes.
Yeah. Alright. Yeah.
I can just make drop-in spacers if we need to.
Okay. Yeah, that'd be best then.
Oh heck, that looks stupid. Alex, if there's ever a time where you're struggling with the nav system for this,
Mm-hmm.
just remember that it's always harder to make EGgBOAT look cool too. I'm struggling here. Look at this box. This is what I'm working with here. What is this?
Wow, that's very box looking.
It's something.
Not, yeah.
Let's check it out from the front. How much better is it look? Oh god.
Does the audience want to see? Should we show them?
Yeah, I'll try to put it over.
Are you able to switch between screens like onto screen share, or is that not how this? I don't know how this stream stuff works.
I'll pull it up on stream really quick actually.
I think there's I found a couple ways to do it. I'm just gonna try to find the easiest one to export the Arduino data.
Gotcha.
So
So we're actually 0.834 outside of our size requirement, but if you recall what they said about size requirements, the antennas can extend beyond that.
right, so we're good.
That's right. That's our only saving grace.
Yeah.
That's it. I don't even, that might not be, oh wait, that might just be because I'm offset. Yeah, I'm probably wrong actually. Yeah, no, we're actually way within it. We're only 15.6.
Okay.
Okay, for you all watching stream, what you should be able to see here is what I'm working with in CAD, which is EGgBOAT. Obviously, we should be up to date right now with how EGgBOAT looks. But if you look in the center of the screen, I'm working on the control box for all of these components, and compared to the rest of EGgBOAT, it looks kind of awkward up there right now. So we're trying to reduce that factor. So you guys should be able to kind of at least follow where I'm looking until we get back to some work. So you can't see it on screen because I'm modeling on a different computer, but you can kind of follow where I'm looking. I'm making some edits to the control board area, adding mounts right now specifically for the control board. So as you should be able to see, there should be some screw mounts built into that system now. Yeah, you can kind of see them poking through where the circuit board lies there, and this kind of exists now on the board. Those are mounts for standoffs to go to. You ready for some more testing over here?
Not quite. I just need to
Okay.
see what some of the stuff
I
is.
will attempt to keep them entertained with CAD.
Still trying to do the. I might have to like install some program to get this stuff plotted or logged. Just want to see what this thing is. First though. That's cool. Arduino does have a built-in like plotter in real time. It plots. It's like plots the values that it's reading.
Oh, that's
So
sick.
1, 2, 3, 4. So that'll be nice for reading, but gotta figure out how to output it or export it.
Bless you.
Oh, thanks.
So what I'm adding now is an upper level platform before the hatch for a gasket to be laid. This will allow some waterproofing to happen.
it'll be a couple minutes. I'm in the process of getting an application. It'll do it, but I still can count some other stuff first. One of which is like Apple's developer app, which is like 8 gigabytes. So
Oh,
it'll be a
interesting.
minute.
Okay.
But then I can download the actual thing.
Okay.
Have you ever used Putty?
No.
It's like a way to that you can. Well, I mean, you can do a lot of stuff, especially like it's like what you'll use if like you use Raspberry Pis like to connect wirelessly, but it can also just like store all of the values. Like you can connect to the serial port that Arduino is outputting,
Yeah.
and then it just like store all of that output to a file
Nice.
easily. So that should solve it for us. Is that one where the phase circuit is going to be?
Yep.
Okay. What do you think a good goal to hit for tonight is? Get everything ready to do the calibration, or do you want to do the actual calibration tonight?
I guess that's up to you. My big goal is getting this box done.
Okay. My big goal is to be able to. I think a good one is if we can just get all the get to a point where we can read values and log it, and I'll set up a spreadsheet where we can automatically do all the averaging and stuff we
Yeah.
need. So I think we can do that. I think what we said.
Okay, I agree. Let's do that. I think since it's getting late, it's also a good time to kind of wrap stream up really quick. I'll allow us to do something faster like to. So. Go back to our camera. Alright, let's wrap this up with some kind of outro, Alex.
Alrighty.
Give them an update where we stand, where we'll be.
Alright, so coming into the stream, we were just starting to assemble everything. We already had all the parts. Jacob had gotten the main stand all laser cut, and everything was starting to be assembled. We just needed to get the antennas on and get everything wired up. So be able to get that done, get it wired up in the first, I don't know, half hour or so, and then write some code to test the results, and we're able to get a really huge result, which is probably one of the big highlights of tonight, that we were able to put the transmitter up near the front, and we were just looking at one of the values, one of the 4 outputs, just to check, and the 4th one, it was consistently getting a certain value, and then when we moved the transmitter back here, it was consistently getting a different value, which is exactly what we want if it's working. That our values are consistent when the transmitter is in a given location, but they're not the same when you change location. That our values will change when the transmitter moves, but when it's in a single location, it'll stay at that value. And since that worked exactly how we wanted, that gives us a ton of confidence that this can actually work. Up till now, we didn't have any sort of testing with the antennas, seeing how those phases change with the transmitter being different. But because that worked, that is huge. I think we probably, like Jacob was saying, we probably understated because we were so focused on seeing getting it work. We understated how huge that was and how exciting. So that was definitely a huge highlight. And then just modeling and coding after that, trying to get ready for the full build and then the calibration.
That's right. And so, Brian, if you're still on stream, a quick request. Since we did understate and we're like completely desensitized to the fact that the system works, and like the revolution that we figured that out, if you could like go back and maybe edit it so that like there's like
Put applause in the background.
yeah, applause, maybe a little bit like confetti in front of the stream, even though like nothing like reactionary happened. Yeah, throw that out there for us.
Yeah, so pretty successful night. Got that huge result, and then just good progress on getting everything ready for the work tomorrow.
Yeah, it's very shocking to kind of just come out with this much, but with this part being successful, we've got a waterproofing layer on the main hull of EGgBOAT drying overnight, and that'll be completely cured by 5 tomorrow, but in the afternoon tomorrow it'll be dry enough to do a full assembly of EGgBOAT, and once that is assembled by roughly around 5 o'clock, whenever that cure is done on the outside hull, we are going to hopefully have enough progress between the system here to do our first navigational water test.
Yep.
So we will literally have a fully functioning EGgBOAT, fingers crossed, tomorrow at 5 p.m. So
Will we be doing some streaming for that, or is that not streaming?
I would like to do a stream at least at some point tomorrow. So for those of you watching, our loyal viewers, stay tuned for that announcement. It might end up being in the afternoon when we do the assembly of EGgBOAT here in the basement. And then if possible, I might move this stream to outside and you guys can actually see a water test live. I know we've done a lot of info sessions and kind of shown videos of that there, but if possible, it'd be great to have a live audience for our first full navigation test. So I'll try to keep everybody posted through with Brian's help with posting on Instagram and Facebook and wherever else that needs to be. So we'll keep you updated. But as for that, that's going to be it tonight. We're going to finish calibrating the navigation system. I'm going to finish the 3D model for the control box so we can keep the electronics away from water. And hopefully, God willing, by tomorrow evening, we will have a functioning EGgBOAT to some degree. So,
The goal.
alright, and with that, we're going to wrap this up. Since it's getting late over here, we're going to finish up some work and catch some shut-eye. So thank you for watching. Please like and subscribe if you did enjoy the live stream. It does really help us and supports our channel, so we do appreciate it. Alright, thank you, and goodbye! Alright, you know, we said goodbye, but like you gotta get up to click the button on the stream, so it's not gonna
Where
be
is
like
it?
right now. It'll be like in 10 seconds. So.
Which one?
Love you guys.
It's over here. It's somewhere. It's
Explosions, random explosions. I blew up the system. It's oh my gosh, help! Oh! Oh wait, I was gonna.